Number theory is a branch of pure mathematics devoted primarily to the study of the integers and integer-valued functions. The German mathematician Karl Gauss said, "Mathematics is the queen of the sciences, and number theory is the queen of mathematics." So, a very important role in mathematics. Here is a very simple problem. Let's look at it in two ways. Now, a lot of number theory is about patterns. If we look at this problem, we can rewrite it as 1976 times by 2007, and because the exponents are the same, to the power of 61. Now the units digit of 6 times 7 is a 2. The only thing we need to figure out now is there a pattern related to the powers of 2? And definitely yes. So 2 to the power of 1 ends in a 2, the units digit 2 to the power of 2 in a 4, 2 to the power of 3 ends in an 8, 2 to the power of 4 ends in a 6. So I'll just write 16. Then notice that the pattern repeats. The units digits are exactly the same. 2 to the power of 6 is 64, 2 to the power of 7, 128, and 2 to the power of 8, 256. So note that the pattern repeats in a cycle of 4. So the closest multiple of 4 to 61 is 60. So 2 to the power of 60, the units digit will be, because 60 is a multiple of 4, the units digit will be a 6. And then the pattern starts all over again. So 2 to the power of 61 will end in a 2. Will end in a 2. And that is then the answer to this question. There's a different method. And that method is to look at each one of these individually. So if I look at this individually, we note that 6 times by 6 is 36. 36 times 6 is 216. And you can clearly see that if I multiply that by 6 again, the units digit of any number ending in a 6 raised to any power, the units digit will always be a 6. That sorts out the first half of this expression. Now, once again, patterns, patterns, patterns. Recognize the pattern. So if we look at the powers of 7, we can do that on the other side. Let's look at the powers of 7. So 7 to the power of 1 is 7, units digit 7. 7 to the power of 2, 49, units digit a 9. 7 to the power of 3, 343. 7 to the power of 4 is 2401. 7, 7. 7 to the power of 5 is equal to 16807. Notice the pattern. Once again, a cycle of 4. And all of these on the left-hand side equal the value on the right-hand side. But we are interested in the units digit. So that was 7 to the power of 7. And lastly, 7 to the power of 8. 576 4801. Notice the pattern. 7931. 7931. Just the same cycle of 4 as we had with the number 2 raised to any power. So if I look at to the power of 61, once again the closest multiple of 4 is 60, and so 2007 to the power of 60 will end in a 1, a multiple of 4. And then the next one is 7 to the power of 1. So this unit's digit will be a 7. So we get the same result, 42, resulting in the same unit's digit 2. Let's identify the term factors. Now, a factor of a number divides into the number without a remainder. In other words, a remainder of 0. So if we have a look at the factors of 12, we know that 1 multiplied by 12 will result in 12. 2 times by 6 and 3 times by 4. All of these numbers are factors of 12. So in other words, 12 has 6 factors. And each one of these on the left-hand side has a friend on the right-hand side. Similar with 30. If I look at 30, 1 divides into 30 times. 2 times 15, 3 times by 10, and then 4 doesn't divide, and 5 times by 6. And all of these 8 numbers are the factors of 30 that divide into 30 without a remainder. Now, something that's quite interesting is once you reach almost, I can't use the word halfway, but if I look at 3 times 4, I will not now start and continue from 4 onwards, because I've already, on the right hand side, I've already got all the numbers bigger than 3 that will divide into 12. The same on the right hand side with 30. I will not continue past 6, because 5 times by 6 results in 30. And there's no numbers in between that I can still investigate, which will be factors of 30. Let's have a look at the factors of 60. Factors of 60. So, I've got 1 times by 60, 2 times by 30, 3 times 20, 4 times by 15, 5 and 12, and then finally 6 and 10. And to demonstrate this, there's no number in between 6 and 10 that can divide into 60 without a remainder. So these are the factors of 60. A total of 12 numbers. Let's look at 150. 150, 1 and 150, 2 and 75, 3 and 50. 150 is not divisible by 4. We will look at the divisibility rules in a moment. Then 5 and 30, 6 and 25. Now we're almost halfway. Let's determine which numbers can still divide into 150 between 6 and 25. And the only one is 10 and 15. And we know that we have all the numbers that divide into 150 without a remainder. We've listed them all, because there is nothing in between these two that can divide into 150. And once again, we get a total of 12 factors if we count them. 12 factors. And here at the top, we also have 12 factors. Now, let's have a quick look at notation. We could say that 5 is a factor of 60. Therefore, 60 divided by 5 is an integer and leaves no remainder. Likewise, we could say that 5 is a factor of 150. Therefore, 150 divided by 5 is an integer without any remainder. In the next section, we are going to look at ways of finding these factors, because what we've done here is quite time consuming. We're also going to look at prime factorization in particular. We have investigated factors of a number. We're now going to look at prime factorization. If we look at 210 over 385 as a fraction, we can, with a negative in front, that doesn't really matter, we can simplify this fraction easily by expressing the numerator and the denominator as the product of prime factors. So 210 is 2 times 3 times 5 times by 7, whereas 385 is 5 times 7 times 11. And now it's easy to see that I can simplify this by simply doing the following, and I've got a simplified fraction in simplest form, minus 6 over 11. How do we go about prime factorization? So let's have a look at 12,600. We find the smallest prime number that can divide into 12,600, and that is 2. So we divide 2 in there, and the quotient is 6,300. Divide 2 once again, and we find 3150. That number is even. The number is divisible by 2, and we find 1575. Now, this is no longer an even number, so 2 is no longer a factor. So if we look at our divisibility rules and we get the sum of the digits 1 plus 5 plus 7 plus 5, which equals to 18, we see that 18 is divisible by 3. Therefore, the entire number is divisible by 3. So we can divide this number by 3. And that is then 5, 2, and 5. 525. Now the question is, what's the next prime number? If I look at the sum of the digits again, 5 plus 2 plus 5, that is 12. 12 is a multiple of 3. In other words, 12 is divisible by 3. And therefore, this entire number 525 is also divisible by 3. And that will then give us, when I divide this, 175. Now, if I look at the sum of the digits now, 1 plus 7 plus 5, that is 13. 13 is not divisible by 3. So that's not divisible by 3. In other words, 175 is not divisible by 3. It's clearly the next prime number is then 5. Clearly divisible by 5, and that is 35. And now it's easy. 5, and the last one is then the last prime factor is 7, and we continue with this process until we find a 1. So if I write 12,600 as the product of the prime numbers, it's 2 to the power of 3, 1, 2, 3, times 3 to the power of 2, times 5 to the power of 2, times by 7. Likewise, we can do the ones we just did finding the factors. We can then take 60 and 150 and do the prime factorization. So, smallest prime number is 2, that's 30. 60 divided by 2 is 30. Once again, 2, 15, and then a 3, a 5, and a 1. So the prime factorization of 60 is therefore equal to 60 equals to 2 to the power of 2 times 3 times by 5. Let me just circle this 12,600 as well. 12,600 is equal to the product of those prime numbers. Let's look at 150. 150, smallest prime number is 2. That will give us 75. 75 is divisible by 3, and that's 25, and then 5, and 1. And that results in 150 equals to 2 times 3 times 5 to the power of 2. All these numbers expressed as a product of their prime factors. Now we're going to look at something really super cool. Is there a way to determine the number of factors without listing them all? So what we could do is we take 60, we take the prime factorization of 60, which we just discovered is 2 to the power of 2 times by 3 times by 5. Now, for the sake of clarity, I'm just going to put a 1 over there. So, how do I determine the number of factors? There's a very cool trick. I take the 2, I add 1, multiply by, take the 1, add 1, take the 1, add 1. And that will give me a result of 12. And that is then the number of factors for 60. And we already know that from the work we've done before. What about 150? 150, we did the prime factorization earlier on. So the prime factorization of 150 is 2 times by 3 times 5 to the power of 2. And once again, for the sake of clarity, 2 to the power of 1, 3 to the power of 1. Add 1 to the 1, multiplied by, add 1, and once again add 1 to give us the total number of factors. How do we generalize this? So, in fancy mathematical notation, we can state that if n is, and these are the prime factors of the specific number n, these are the exponents, in other words, the powers of those prime factors. So, if n is equal to this, and this is the factorization of n into prime powers, then n has a plus 1, b plus 1, c plus 1, and complete until the end factors all together. So that's a super cool method to discover the number of factors without actually listing them. So let's have a look at one that is particularly cool. What about 1,000,000? Now we know that 1,000,000 can be written as 10 to the power of 6. But that is not the prime factorization of 1,000,000. What is the prime factorization of 1,000,000? It's very easy to derive that it's 2 to the power of 6 times by 5 to the power of 6, which then is 10 to the power of 6. And both of these are prime. So, how many factors does 1,000,000 have? Add 1 to 6, 7. Add 1 to 6, multiplied by 7. So, a result of 49 factors, which would have been very difficult to calculate if we did not have this super cool trick. Now we are going to investigate the two terms lowest common multiple versus highest common factor. So we're going to start off with our very same two numbers, 60 and 150. We're looking at the lowest common multiple. So first let's write down the multiples of 60. 60, 120, 180, 240, and then 300, 360. Let's end it there. And then 150 is 300. And the next one will be 450 and then 600. So those are the multiples. Multiples. Now we have to look at common multiples. Let's circle them. Common in both. That is 300 at this point and 300. And those, so they are common. And the lowest one that's common is 300. So the LCM for the LCM written as the LCM 60 and 150 equals to 300. Let's look at the highest common factor. So highest common factor, once again 60. We already found the factors of these two numbers, so I'm just simply going to list them. Let's list them. 60 is 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, 60. The factors, 150, also 12 factors, as we know by now, 5, 6, 10, 15, 25, 30, 50, 75, and 150. Now, this time we're looking at the highest common factor. So let's first circle the common factors. 1, 2, 3, 5, 6, 10, 15, 30, and that's it. What's the highest common factor? Notation. The highest common factor, notation, is 60, round brackets, and that equals 230. So that was quite a time-consuming way to find the lowest common multiple and highest common factor. Let's look at a more effective way. So if I list the prime factors of 60, 60 is equal to 2 to the power of 2 times 3 times 5. Whereas 150 is equal to 2 times 3 times 5 to the power of 2. Now here is an excellent algorithm to find the lowest common multiple. To find the lowest common multiple of 60 and 150, we take each factor. So we've got a 2, we've got a 3, we list them all. We absolutely list them all. And then we take the largest value. So in other words, we take the largest value of 2 and 1. Where did the 1 come from? There's a 1. We once again take the largest value of 1, that power 1 and 1. There's also 1. And then we take the largest value of 1 and 2. And if we look at that, that is then 2 to the power of 2 times by 3, and then 5 to the power of 2. Right, so that is then, that will give us the very same result we found, that is 300. So that's the more effective mathematical way. If I look at highest common factor, I do the opposite. Highest common factor, 60 and 150. And this time I write down all the factors, all of them, in both numbers, list them all. This time I take the smallest of 2 and 1. The same powers, 2 and 1. Smallest of 1 and 1, and the smallest of 1 and 2. Should there have been, let's say, argument's sake, a factor that did not exist in both, then that particular factor that doesn't exist in the prime factorization of the one number will have a power of 0, and then 0 will be the smallest. And of course, 7 to the, let's say it's 7 to the power of 0, then is actually 1, which won't have any effect on the HCF. So if we look at this final result, smallest is 2 to the power of 1 times 3 to the power of 1 times by 5 to the power of 1, which will result in the 30. Therefore, this is the most effective algorithm so far to find the lowest common multiple and highest common factor. Something very interesting is that the lowest common multiple of 60 times by 150 times by the highest common factor of 60 and 150, that will result in 60 times by 150, which in this case equals to 9,000. And if I look at 300 times by 30, that is then also 9,000. Just an interesting fact on this side. And there is yet another method to find the highest common factor, which is called the Euclidean algorithm. So let's briefly have a look at 60 and 150 again. We write down 150 and 60, and we divide 150 by 60. Now that we know is then 150 is equal to how many times? That is 2 times by 60 and a remainder of 30. We confirm that 30, the remainder, is less than the divisor. So 30 less than 60. And we start the process again. We divide 60 by 30. And that then gives us, 60 is 2 times by 30, remainder 0. What is the HCF, the highest common factor? Once we get to a remainder of 0, the previous divisor before a remainder of 0 will be the highest common factor, and we've already confirmed that result as well. Let's look at two numbers where it's slightly more complicated. So we are going to take the numbers 26 and 62. We're looking for the highest common factor of 26 and 62. Round brackets as the correct notation. And we start off by dividing 62 by 26. And we find that 62 is equal to twice 2 times 26 plus a remainder of 10. And we confirm that 10 is less than the divisor. Then we take 26 divided by 10, and that is 2 times by 10 and a remainder of 6. 6 is less than 10. We start the process again. 10 divided by 6 is a remainder of 4. 4 is less than 6. 6 divided by 4, that will then be 6 is 1 times by 4 plus a remainder of 2. 2 is less than 4. 4 divided by 2 will finally result in a remainder of 0. So what is the highest common factor? It is the remainder before we find a remainder of 0. So in this case, the highest common factor will equal to 2. And that is then the Euclidean algorithm, yet another way of finding the highest common factor. We have to tackle this problem step by step. So we know that we're looking at the natural numbers less than 1,000. We have to find the largest number that has the following properties. If it's divisible by 3 and 7, the number must be divisible by 21. The sum of its digits is 15. So let's look at the 2-digit numbers. That's multiples of 21. That's 21, 42, 63, and 84. Now none of these have a sum of 15. So therefore we know it must be a 3-digit number. 3-digit number. Let's use clue C to help us with that. If it's a 3-digit number and the product of its digits is 48, what can that possibly be? So that could be a 1, a 6, and an 8. Let's try with 2, 2, 3, and 8. We could have 2, 4, and 6 as well. And then we could have 3, a 4, and a 4. And that's then the possibilities that we've got. So if we list these, if we look at these, only the first one has a sum. If I add the sum of the digits or get this, obtain the sum of the digits is 15. So only the first one has that quality. So if I arrange the numbers, it could be 168, 186, 618, 681, 816, 861. Now there is a trick to find out whether a number is divisible by 7, but the trick is more work than actually just quickly taking the numbers and divide them by 7. So we know that all these numbers are definitely divisible by 3. But because of the fact that the sum of the digits is 15. But what about 7? So if we divide by 7, we will find that only 168 and 861 are divisible by 7. And of these two, the largest number that has all of these properties will then be 861. Question 2. The positive integers 30, 17, 2 and n have the property that the product of any two of them is a multiple of the third. What's the smallest value of n? So we can write that as 30 times n is a multiple of 72. From everything we've done so far, we know therefore that 30n divided by 72 is an integer, no remainder. And we can divide top and bottom by 6. 5n divided by 12. And we can do the exact same thing by saying that 72 times by n is a multiple of 30. Therefore, 72n divided by 30 is an integer. And I can then divide top and bottom again by 6, and I get 12n over 5 is an integer. From both of these results, we can see that n must be divisible by 12 and 5. How do I know that? 5 is not divisible by 12, so n must be divisible by 12 in order for this to be an integer. The same argument here. 5 cannot divide evenly into or without remainder into 12, so n is divisible by 5. So that means that n must be divisible by 60. Must be divisible by 60. All we need to check now is the following. So we're now going to check whether this all results in whether this will make this true. So if I take 30 times by 60, that's equal to 72 times by 25. So yes, if n is 60, so let n equal to 60 as an initial attempt, we see that 30 times by 60 is a multiple of 72. Likewise, 30 times by 72 is 60 times 36. So that's a multiple of n. And lastly, 60 times by 72 is 30 times by 144. So all three of these, if I multiply 30 and 72, it's a multiple of 60. Multiply 30 and 60, it's a multiple of 72. Multiply 60 and 72, it's a multiple of 30. So the smallest possible value of n is equal to 60. Now, from what we've discussed before, we know that the number of factors can be expressed as a plus 1 times b plus 1 times by c plus 1, and where a is the powers of the prime factors. Now, if a number has 5 different factors, it means that this product must equal to 5. But 5 is prime, so it's only divisible by 5 in itself. That means we're looking at a single number to the power of 4. And that's the only way that we can apply this and say that the number has 5 different factors. So that will result in 2 to the power of 4 is equal to 16, and 3 to the power of 4 is equal to 81. And we'll stop there, as 4 to the power of 4 is greater than 100. So there are only 2. The answer to this is there are only 2 numbers with exactly 5 factors. The next 2 slides cover the divisibility rules. You can go over them in your own time. The divisibility for rule for 7 is quite complicated in the sense that it could possibly take more time than doing the actual division by 7. The divisibility rule for 11 is very cool. You add alternate digits, in other words, every other digit. If the 2 numbers are equal, then the number is divisible by 11. if they are different, we subtract the numbers, and if the difference is divisible by 11, then the entire number is divisible by 11. Let's quickly look at what we mean by saying this. If I look at a number like, let's say 1364. So I've got 1364, we add alternate numbers. So we add 1 and 6 will give us a 7, 3 and 4 is 7. So these two numbers are the same. This means that this number is divisible by 11. Let's look at 913. We add alternate numbers. So we add 9 and 3 to get 12, and the 1 is in the center. 12 minus 1 is 11. 11 is divisible by 11, so 913 is divisible by 11. A 4-digit number, add alternate digits. 3 and 2 will give us 5, 7 and 9 will give us 16. The difference is 11, so the entire number is divisible by 11. A very interesting problem. Let's read it. If you write the integers 2, 3, 4, 6 and 8 in every possible order to form 5-digit numbers, how many of these numbers will be divisible by 11? Now, what does that mean? 5 digits, 1, 2, 3, 4, 5. Because there's 5 digits, that means there's 5 to choose from for position 1, 5 to select from, then 4, then 3, then 2, then 1. And that gives us a total of 120 different options. So to write each one of them down will be a very time-consuming exercise. Is there a better way to find out how many of these will be divisible by 11? Now let's just randomly take 6, 4, 3, 2, 8 for argument's sake. And we find that this is divisible by 11. So that is 5, 8, 4, 8. So that's a lucky guess. But then again, if we rearrange and we investigate 4, 6, 8, 2, 3, that is not divisible by 11. Now, from our divisibility rules, we know that we have to take the alternate numbers. So in this case, if I look at the alternate numbers, let's say that the numbers in position, let's say the number in position 1 plus position 3 plus position 5, let's say that total is x. And then the numbers in position 2 plus position 4, let's say that's y. So if I say x minus y, I look at x minus y must be a multiple of 11. First of all, equal to a multiple of 11. That's the divisibility rule for 11. And secondly, we know that x plus y in this case is, if I look at the sum of the digits, 6 plus 4 plus 3 plus 2 plus 8, that will give us 23. Now, what could x minus y possibly be? Because this number is odd, x minus y cannot equal to 0. And then if we look at x minus y equal to 22, that will only be possible if we could possibly say 23 minus subtract 1, which will then equal to 22. But that's not possible because the total is 23. We do not have the sum of our digits won't allow for us to find 22. So the only option is x minus y must equal to 11, and we know x plus y is equal to 23. This allows for two beautiful simultaneous equations, and that gives us 2x is equal to 34, meaning that x is equal to 17 and therefore y must equal to 6. The only way we can obtain that is if we use in position 2 and 4, we use a 2 and a 4, or we use a 4 and a 2 to equal 6. The rest of the digits will then add up to 17. What's the rest of the digits? That will be a 6, a 3, and an 8. So I've got 3 numbers to choose from for position 1, 2 to choose from for position 3, and 1 to choose from for position 5. That allows for 6 options, 6 different numbers. What could that possibly be? That could be, we could arrange them as 3, 6, 8, 8, let's do this systematically. 3, 6, 8, 3, 8, 6, 6, 8, 3, 6, 3, 8, 8, 3, 6, and 8, 6, 3. 6 different options. And that will then repeat. So that is for the 2 in position 2 and the 4 in position 4. That will repeat if we swap the 2 and the 4. And that gives us a total of 12. A beautiful way to find how many of these numbers, 120 options, 12 of them will be divisible by 11. If x and y are 2 digits and the 5-digit number 30xy5, all individual digits can be expressed as the product of 225 times by n. Find all possible positive integer values of n. So we know for sure that this number is divisible by 225. Let's prime factorize 225. Now 2 plus 2 plus 5 is 9. So the sum of the digits equal to 9. That means the number is divisible by 9 and therefore divisible by 3. So if we divide by 3, we find that we can divide by 3 once again, and then 5 and 5. So we can also write this number as, we can say that this number is divisible, so 30xy5 is divisible by 9 and 25. Why do we look at 25? An interesting pattern emerges when we look at a number that's divisible by 25. First of all, a number that's divisible by 25 ends in 0, 0 times by 4, for instance, or 25, 50, or 75. These are the last 2 digits of a number that is divisible by 25. We can test that by saying 25 times 1, 25 times 2, 25 times 3, 25 times 4, and then the pattern starts repeating again. So that means that y could potentially be either a 2 or a 7. Let's plug that in. So we know now that this number must also be divisible by 9. So let's have a look. 3 plus 0 plus x plus y plus 5 is equal to 8 plus x plus y, which must be a multiple of 9 in order to be divisible by 9. So if we now say let y equal to 2, we find that we've got 8 plus x plus 2 is 12 plus x. Therefore, x must equal, not 12, that's 10. 10 plus x. Therefore, x must equal to 8. X equal to 8 in order for the sum of the digits to be a multiple of 9. if we state let y equal to 7, we have 8 plus x plus 7 is 15 plus x, and then the only value for x is a 3. And we're looking for the values of n. So we are going to say 2 to 5n. So we've got 3, x is equal to 8, y 2, 5. And if we divide that by 225, we will find n. That will give us n if we simplify this fraction. And on the other hand, we will also have 30375 divided by 225 to give us another value of n. Now, because of the fact that we don't have calculators, we could simplify this manually. So let's have a look. Let's do the one on the left hand side. We can see that both of these will be divisible by 5. So let's start off top and bottom, divide by 5, and we will find that so divide by 5, divide by 5, and that will give us a value at the top of 6165 over 45, and we can divide top and bottom by 5 once again to simplify this fraction to 1233 divide by 9. Now, if I look at the sum of the digits, 1 plus 2 plus 3 plus 3, that will give me 9. So, top and bottom is definitely divisible by 9. So, if I divide the top by 9, the bottom by 9, I will find that I get an answer of 1. Let's carry there, I'll carry a 3. That will give us a 3 times 9 to give us 27, and then 63 divided by 9, 137. So one value of n is 137, and we can follow the exact same simplification process over here to find another value of n that will be 135. Let me use, that will be 135. So our final answer here is 137 and 135. This problem is quite tricky. On the right hand side, I've included a picture of a function where the function is initially decreasing, at the turning point increasing, decreasing again, and then increasing. But in this question, we're dealing with a 5-digit number whose digits are strictly increasing from left to right. And the question is, what's the smallest prime number that does not divide any number in this set? So if I have a look at, let's have a look at the prime number 2. It's very easy to find 1, 2, 3, 4 strictly increasing in an even number and divisible by 2. The sum of these digits, 1 plus 2 plus 3 plus 4 plus 6 is 16, therefore not divisible by 3. But if I subtract 1, I find a sum of digits of 15, which will then be divisible by 3 and by 5. Now, to find the next prime number that or to find the next prime number is 7. Let's see if we can find a number strictly increasing that is divisible by 7. Now we'll have to play around a bit and see that 1, 2, 3, 4, 5. Let's divide that by 7. That's 1, and that is 7, remainder 4, 6, remainder 2, 3, remainder 4. So let's try, as a starting point, let's try 1764 times by 7. So that's 28, 4, that is then 44, and 7 times 7, 49, plus is a 3, so far so good. And then 1, 2, 3, 4, 8. That's super cool. We found a number that's divisible by 7 and the digits are strictly increasing. Let's list it like this: 1, 2, 3, 4, 8, divisible by 7. The next prime number is 11. We are now going to prove mathematically that this number, we are going to prove that a number where the digits are strictly increasing is not divisible by 11. So let's start off by saying that because of the strictly increasing, we know that we have the following property. So let's say we start by contradiction. We're going to prove this by the method of contradiction. So because we are going to assume that this number, that there is a number that is divisible by 11. Assume A, B, C, D, E exists and it is divisible by 11. That then means if we use the rule of divisibility by 11, that the sum of the alternate digits A plus C plus E minus B plus D, the other digits, must be a multiple of 11. That's according to the divisibility rules. Now, if I look at this, and this must be a multiple of 11, the difference must be the difference could be 22, 11, or 0. 0 is not possible because of the fact that these digits are strictly increasing. 0 is not possible. Now, if I look at the largest value of A plus C plus E is 9 plus 8 plus 7, and then minus, so this difference, the largest value for this difference is 21, which is less than 22, so that is not an option. Then if I look, so we know now that A plus C plus E minus B plus D must be equal to 11. If we investigate that, we see that we can rewrite this as B plus D plus 11 is greater than or equal to. Now, if I look at B, B must be at least 1 more than A. And D must be at least 3 more than A. So B plus D must be greater or equal to A plus 1 plus A plus 3 plus 11, which simplifies to 2A plus 15. So we could say that A plus C plus E, which is equal to B plus D plus 11. Remember, from here, A plus C plus E is equal to B plus D plus 11, must be greater or equal than 2A plus 15. If I simplify that, I find that C plus E must be greater or equal than, subtract the A both sides, A plus 15. And we know that A plus 15 must be greater or equal to 16. So if I look at that, and I look at which value will give me 16, that means that C and E, C must equal to 7, and e must equal to 9. That is basically the only solutions to find 16. So, if I then write A, B, 7, 8, 9, that is then my number. So I can now say that from here that A plus 7 plus 9 must equal to B plus 8 plus 11. Let's investigate that. That if I simplify both sides, I get that A is equal to B plus 3, which is greater than B. And that is a contradiction. So that means that this number with strictly increasing digits from left to right will never ever be divisible by 11. Here is a new type of problem. N is a positive integer such that 7n minus 13 divided by n minus 4 is an integer. So this fraction must represent an integer. How many such n are there? Now we start off by looking at this fraction. So this fraction, we say that this is improper. The reason for that is that the highest power of the variable is 1, top and bottom. And if it's the same power or the numerator is bigger, then the fraction is improper and we perform long division. So let's look at the long division algorithm. Divide by n minus 4. So the purpose of this question is not to teach you long division. But I'm just going to show you. You just look at the first two as long as you arrange the variables in decreasing order. So 7n divided by n is 7. You say 7 times by n is 7n. 7 times by minus 4 is minus 28. And like we performed long division in primary school, we now have to subtract this. 7n minus 7n is nothing. Minus 13 minus 28 will result in a positive. So in other words, minus 13 subtract negative 28, which is 15. We can no longer continue with this algorithm as 15 is a constant and we need another n in there to continue the division process. So I can say that 7n minus 13 is equal to 7 times by n minus 4. So where did I get that from? 7 multiplied by the divisor plus a remainder of 15. Alternatively, so I can now rewrite this fraction as 7n minus 13 divided by n minus 4 as 7 times by n minus 4 divided by n minus 4 plus 15 over n minus 4. This results in an integer. 7 plus 15 over n minus 4. So this is now an integer. All I need to ensure is that this will also have an integer value within the constraints. What's the constraints? N is a positive integer. And we want to know how many n's are there. So we know that n is greater than 0. And n minus 4 is therefore greater than minus 4. So all we're interested in is the factors of 15. Let's look at the factors of 15. That will be, so as long as it's got an integer value, so it's minus 15, minus 5, minus 3, minus 1, and then also 1, 3, 5, and 15. So these are the factors and they represent n minus 4. So the ones that I can use is -3, -1, 1, 3, 5, and 15, where n-4 will then be greater than -4. That then means we can find the values of n, but that's not the question. The answer to this question is therefore 6 solutions. 6 solutions for n. Problem number 8. We want to find the value of k plus l if k and l are positive integers and k plus l plus kl is 54. If we look at this problem, we can see the fact that k is part of kl complicates the issue. So if we could take k out as a common factor from k plus kl, we end up with 1 plus l, and that is equal to 54 minus l. So k is 54 minus l over 1 plus l. So we can once again see that this is an improper fraction. The reason being that the degree of L, top and bottom, is exactly the same. So we are going to perform one long division again, 54 minus L divided by 1 plus L. And we rewrite this in the correct format. Minus L plus 54 divided by 1 plus L. Or let me rather say L plus 1. So L divides into minus L minus 1s. Multiply the minus 1 with this divisor and we end up with minus L and minus 1. And that is then, we subtract. So minus L subtracted, or subtract minus L, is minus a negative, which results in nothing. And 54 minus minus 1 results in 55. So we can rewrite this as 55 over 1 plus L minus 1. Now, we know that k is a positive integer. That means, once again, that 55 over 1 plus L minus 1 must also be an integer. And that only happens when 1 plus L, same concept, 1 plus L must be a factor of 55. We know that L is also greater than 0, so k greater than 0, L greater than 0. So that means that L plus 1 must be greater than 0. So L plus 1 could potentially be 55, 11, or 5. If L plus 1 equals to 55, that means that will result in k equal to 0 if L plus 1 is 55. So that will result in 1 minus 1 over here, which is a contradiction. So L plus 1 cannot equal to 55. And if, let's have a look at L plus 1 equal to 11, L plus 1 equal to 11, that means that L is then equal to 10. And if L plus 1 is equal to 5, that then means that L is equal to 4. So if we test these two and we have to find the value of k, let's see what that will then result in. To find the value of k, we will have k plus 10 plus 10k equal to 54, and that is then 11k equal to 44, and k is equal to 4. K plus L is then equal to, k plus L is then equal to 4 plus 10, 14. In the scenario where L is equal to 4, we'll have, so here let's just say L equal to 10, and here L equal to 4. L equal to 4. And that will then be k plus 4 plus 4k is equal to 54. So 5k is equal to 50, and k is then 10. And once again, we get the exact same result, k plus L equal to 14.